Exchange from Weizmann, and the Gilbert Institute from Barcelona. By the way, Gilbert is the name of the father of Steve Gilbert, Arthur Gilbert, also a mathematician. And also administrative announcement. In case of a siren, there's nothing we can do. So we can resolve the issue.
So we should not leave, right?
Yes, we should not do it. Because to get to any safer room, we do faster outside, which is less safe than sitting inside the building. But I hope Weizmann Institute has some protection.
My theory is that the art is paying to Putin because
so as far as I understood, the goal of that
went up drastically.
So I just understood from Sasha that the goal of that attack was to keep Sasha in Israel.
And Dennis outside.
Yes, this was a misconception. So last time, at least some of us met for Yosef's 72nd birthday, and Erez Lapid made an impressive list of Joseph's works. And apparently this long and impressive list was incomplete. Every other speaker was started by, I would like to mention another paper of Bernstein. So I decided that I will not even attempt to do this. But Andrei and I thought a little bit, and we decided that what we should mention is that besides this huge contribution to mathematics, not only for papers, but also for discussions with mathematicians worldwide, Yosef is one of the pillars of Israeli mathematics. And, this is one more reason to celebrate. I should also say that by participating in organizing this, while Andrei did more than me, I'm going against the advice of two Sashas. One of them gave me advice never to organize conferences. And as any universal advice, it is absolutely correct and very hard to follow. The other advice was specifically against 80th birthday, because it was strange that last time we organized 72nd birthday. And there were many guesses why. And actually it was just our procrastination. But Sasha Goncharov had better explanation. He said that, 72 is divisible by 18. And 18 is higher. And but by this logic, he suggested that you should only celebrate years divisible by 18, and the next one should be 19. But we decided that in order of Joseph Bernstein, who defined so many abstract structures, we can do higher mathematics and do multiplication. So I'm very glad to present our first speaker, Vladimir Hinich, and also thank him for changing slots with Dennis. And the last thing I should say is happy birthday. Many happy returns, many conferences for us, and many more mathematics. Yesterday,
You should turn this on.
yes.
Not in this problem.
Let's see how it
Works.
Yeah.
Do you hear me?
Yes.
So due to yesterday, maybe it's better without.
I think maybe you should turn off that one. Maybe that's the one.
I don't know.
Yeah, I think now it's working.
Okay, so due to yesterday's rocket attack, the organizers decided to make the first talk more down to earth. So they replaced Dennis's talk with this one. Okay? I want to thank also the organizers to providing the blackboards that are not very big, so I will be able to feel them, even though I usually feel that I have nothing to tell. Well, that's not very important. So I'm going to tell about my joint work with Maria Gorelik. And it has something to do with the centers. You don't see it?
Just a
Maybe the blue one.
Okay. And it has something to do with description of centers of Lie superalgebras. The results are not new. But the story is a little bit reminiscent to the famous story about Shepard-Todd theorem, which was first proven just on basis of knowledge of classification of complex reflection groups. And then a year or so later, there was another proof based on homological algebra, commutative algebra, and things like that. So here the results are new, and probably the correct reference is papers by Ian Masson. But somehow we found a way to nicely present them, and maybe generalize, which is less important. So here is a setup. Setup is very elementary. Let V be a complex vector space, and let L be an equivalence relation. We define invariant functions. Well, in an obvious way, the set of polynomials such that f of x equals f of y for any pair xy in L. Okay. Functions that have the same values at equivalent points. Of course, the first example is given by a group acting on V, and then the equivalence relation is x is equivalent to S of x. Okay. And we know the invariant subring in this case is just what we usually call invariant subring. And it has some very obvious properties. The properties I will discuss are much simpler than property of being a polynomial ring. Just the correspondence between maximal ideals here and maximal ideals in C of V. So we know that any maximal ideal in the invariant subring, I will write down any equivalence relation, lies under a maximal ideal in C of V. It means for any maximal ideal, there is a point where it vanishes. The second property, well, you can formulate them in one, but somehow it's better like this. The equivalence relation is uniquely defined by this invariant subring. So X is equivalent to Y if and only if for any F in the invariant subring we have F of X equals F of Y. So these are two properties that interest us. Of course, they hold for the action of finite group. Of course, they cannot be true for any equivalence relation, but we are not interested in any equivalence relations, but with very special ones. Those that appear in superalgebra business.
Can you repeat the two properties? I missed them.
Maybe right and larger.
You have a polynomial ring and you have a subring. This defines an equivalence relation. So if this subring is obtained from equivalence relation, the question is whether you get the same relation back. It's a sort of closure, right?
So this is the property?
Yeah, this is the property. Yes. Why is it interesting in Lie superalgebra's business? For some special examples, you get a description of center of enveloping algebra of Lie superalgebra via Harish-Chandra isomorphism. And of course, you want to know something about representations of these Lie superalgebras. Knowing the center, knowing characters of the center, you can say something about blocks of representations. So that's an interesting question. And what I want to tell now about two micro discoveries about this business. I will just list them, and then we will discuss each one of them.
Did you say that these two properties hold for any finite group action?
Yeah, that's of course well known. Okay. Micro I will discoveries. The first is a description of a very beautiful class of equivalence relations.
How do you call relations that satisfy this property? Or you don't call them?
I call them Lagrangian. Which will include actions of finite groups. if it finite group of orthogonal transformations. And will include all equivalence relations that are relevant to to description of the centers of Lie superalgebras. Pardon?
About reductive groups. Various reductive groups.
Reductive groups? No.
You will not satisfy that condition.
No, only finite groups. The second micro-discovery is maybe more pedagogical, and it has something to do with Joseph. About 20 years ago, he taught a course in algebraic geometry at Tel Aviv, and he told me that he finds the idea of starting the course with the notion of scheme very unnatural, and much better approach can be found in Kemp's book on algebraic geometry, where he uses formalism of spaces with functions. I was very upset by this idea at the time, but now I find it very nice idea, and actually it turns out that Kemp's approach is very good for these types of problems. So I will be using it in order to study geometrically these invariants, which means study factors V over L of the type we will discuss. So these factors, of course, are not algebraic varieties. They are some very strange beasts, but still elementary sheaf theory of the type that suggests Kemp's definition is useful in proving things. So these are two micro-discoveries.
I was specifically saying they're not schemes, so I maintain they're not any space that algebraic geometers like to study.
Well, I haven't asked all algebraic geometers, but you will see, they are definitely not schemes. So to understand what we are talking about, let me give the simplest example. Which actually appears in Lie superalgebra theory. But I won't be talking a lot about Lie superalgebras. But for those who are interested, this is GL11. So V is two-dimensional. And the equivalence relation is generated by the requirement that any multiple of V is equivalent to 0. So you take two-dimensional affine space and you contract one line to a point. It's not a scheme, believe me. Oh, I think it's not a scheme. Let us write down the algebras. Okay, we have C of V, which is C of xy. I think of x and y as, well, dual basis, right? And our invariant subalgebra is C plus y times xy, if I'm not. Well, it's subalgebra of polynomials in two variables that does not contain positive powers of x.
Zero power.
Pardon?
You mean zero power or positive power?
Positive power. Zero.
Without y.
Yes, positive power of x means without y. Okay. So it's not an algebra of finite type. Of course, spectrum of this would be a scheme.
Specific. Yes.
Pardon?
No, V liter is one of the two generators.
No, this is capital V, of course. And this is, okay, I write them differently, by the way. Okay? So, if we want...
You said what you wrote, why is what you said the same as what you wrote? What about what, the monomial y should appear in the limit that you said? That
I am saying that this is the collection of sum Cij x to the power of I, y to the power of j, where Ci0 equals 0
Yeah,
for
I think you should write C plus y times C of xy.
Well, this is, for me, the ideal generated by x and y.
But then it won't contain y, which it should contain, right?
the idea y times the idea generated xy does not contain the monomial y, which is a problem because you want to.
Right.
Write y times C of xy.
Absolutely. Pasha, you're right. Yeah. Okay. Very well. So it's not difficult to find out, to describe all maximal ideals of A. We just should consider cases. Because this space is a sort of stratified something. So we consider maximal ideals that do not contain y. Well, that's easy. They correspond to maximal ideals. I will write like this, spec. You understand what I mean? Of the localization by y, which is a very meaningful thing, which is the same as C of xy localized by y. So there is no this is a sort of generic thing, and there is a special thing for maximal ideal containing y. But then we mod out by the ideal generated by y. And it's easy to see that this is a ring that has only one maximal ideal. And if I'm not wrong, it's maximal ideal of square 0, but infinitely generated. So we deduce from this very elementary example that actually the problem is very simple, but we have somehow to organize everything to make induction. There is a sort of stratification, and we should think about it. Okay? Well, that's it about the example. Let me now start describing this beautiful class of equivalence relations. Well, that is not good, I have to say. Maybe that is better. No, this blue thing is not good. Well, this is a very elementary linear algebra. So, if you haven't studied it well at school, it's a good opportunity. Okay. Now we have, this is called Lagrangian equivalence relations. So we have V, and we wanted to have a, well, not the inner product, symmetric bilinear form. Non-degenerate, of course. Now I defined another form on V times V. If you think it's symplectic, you're wrong. It's also symmetric. B of V W V prime W prime is V V prime minus W W prime. Okay? Well, now I consider linear vector subspaces of V times V as linear relations. Okay? So, definition. A linear relation is isotropic if B on L is 0. Well, since it's a symmetric form, you should just verify that for any VW in L, the bilinear form with itself is 0, which means that VV is WW. That's isotropicity. And of course, it's Lagrangian. If it is maximal isotropic. That's it. Example. Choose an endomorphism and take L to be its graph, which is the set of pairs V alpha of V. We immediately see that L is isotropic if and only if it's Lagrangian. If and only if alpha is orthogonal. Okay, so for me, a Lagrangian relation, linear Lagrangian relation, is a sort of mild generalization of an isometry. Maybe it's worthwhile to give another example, which will also appear later. Linear relation mean, yeah, it's just vector subspace. That's it. Of course, graph is always of half dimension, so another example. Let V0 inside V be co-isotropic subspace, which means that V1, this is my standing notation for orthogonal complement of V, is inside V0. Then the following relation is Lagrangian. Pairs of elements of V such that they belong to V0 and their difference belongs to V1. Okay, so these are our building blocks. But we have to know how to build things, right? Here is a very obvious lemma. Everything I am telling is very, very simple, but there are some absolutely obvious things. I will prove them because, yeah, very easy lemma. Sorry, I forgot to tell. There is an operation between relations called composition. So let me start with definition. If L prime are relations, their composition is the set of V W in V times V such that there exists U in V with VU in L and UW in L prime. Well, everybody knows this. The only argument is whether we should define it like this or opposite. Maybe opposite is better, but I've got accustomed to this. This is not important. Okay, composition of relations. Is composition the correct word? Or is this convolution? Convolution.
If the relations are functions, then it is composition, yes?
Yes, but in the opposite direction. But, well, that's really not important. Okay, so lemma that I wanted to prove. Pardon? Sorry, they are not equivalence relations, they are relations. If I said equivalence, this was just, I haven't had enough coffee, that's all. These are relations. Relation is a subset in V times V.
A subset?
Yes. For relation, in my opinion, no. if you want relation to satisfy some properties, you require them. If you don't want, you don't require them. Okay? Well, no. If you are talking about equivalence relations, well, I taught this once at the university. So there are three conditions: reflexivity, transitivity, symmetry. That's it.
Also, the Lagrangian doesn't imply equivalent relation, right?
Almost never. Almost never. Well, I will define Lagrangian equivalence relation, but it won't be linear. Sorry. Okay, so here is the lemma, which we will prove together. If L and L prime are, how I call them, isotropic, which means linear isotropic, then L composition with L prime is isotropic. Okay? Proof. VU belongs to V means V equals U. UW belongs to V L prime means U is equal to WW. Together we deduce that V is equal to WW, which means that that the composition is isotropic. That's it. This wouldn't be so easy if we had symplectic form, but for symmetric form, everything is easy. Okay? Pardon?
Is it true for symplectic?
I think no. But fortunately, we are in a better world. Okay, so composition of two guys is, isotropic. Of course, in a moment I will say that the same holds for Lagrangian, and this is, I think, a remarkable fact. It's not difficult, but it requires more writing than I'm ready to do. Let me, before this, let me, okay, I will formulate a result which will add a few details to this fact about good behavior of. Okay, so proposition. So L is Lagrangian. Linear Lagrangian, I mean. Let us denote Ki for I1 and 2, kernel of the projection. Okay? Then, first, dimension of K1 is equal to dimension of K2. This is what allows us to call this atypicality of L. This is atypicality of a linear Lagrangian relation. And second, P1 of L is P1 of K2 orthogonal. So the image is uniquely different. So, by the way, in particular, this means that P1 of L, and of course the same is true for P2, is co-isotropic in V. Because it contains, this is part of this, of course. Okay? Well, and now I am ready to say the proposition L prime Lagrangian implies that L prime is also Lagrangian. So it's an interesting construction. I don't know. It's so elementary, I can hardly believe that it hasn't been known. But, well, maybe you will say that it has been known. I don't know. So you have orthogonal group, and you complete it, you a little bit extend it with Lagrangian linear relations. And Lagrangian linear relations form a monoid. And this embedding, of course, respects the same, well, up to my stupid definition, up to changing the order of operations. So it's a sort of completion, I don't know, of the orthogonal group, which is monoidal. Pardon?
It's used in the theory of tensor categories.
Ah, it's used. So, okay. Well, nice to invent something, something known to be important.
If you take category of vector spaces graded by a Billian group, finite Billian group, then invertible bimodals over this correspond to elements of orthogonal group of this group plus dual group. But there are no non-invertible bimodals, and they correspond to something.
Ah, well, very nice.
Adjudicality is dimension of K1 and K2?
Yes, it's their common dimension. So to understand better what we are talking about, let us describe atypicality 0. Atypicality 0 means that L is a graph of something. So L is graph of orthogonal transformation. Those are invertible elements. Yes, exactly. Okay. Whether I forgot something? Well, another theorem, which I don't know whether it's important or not, but it's nice. You remember I denoted E V0, a very special Lagrangian relation constructed by a co-isotropic subspace V0. So L is V0 if and only if L is idempotent. And maybe it's worthwhile to add, for any Lagrangian L, if we compose L with the inverse is just, well...
in the plane or in general?
Pardon?
V0 is not a vector, it's a subspace.
No, V0 is co-isotropic space. It's defined here.
This
Okay.
is important, but not important. So you
Well, this is obviously important, but converse is also true. Not very difficult. There is nothing very difficult here. Okay, so this guy is, of course, idempotent, so we can easily believe that this is E something, and this is E of P, I think 1, but maybe 2. It depends on the order of these guys. Of it.
You write inverse, but you don't mean inverse in the monoid, because it's something else.
I mean not inverse in the monoid, but what you call inverse relation, just replacing two copies of.
Can you
Okay.
explain what's going on?
But it is inverse if it's invertible.
Can you explain what's going on if V is two-dimensional, or it's too much to ask? How does monoid look like? Some compactivity,
I haven't thought.
Do we have topology on the monoid? If one is suggesting that it's a compactification or
Well, it's a very nice algebraic variety, I assume. Yeah,
It's complete, yes.
I believe it's complete, but we should ask Pasha. I was sure that it's very well known thing. Yeah,
So it's some compactification of the orthogonal group, which is not a group anymore.
it's some compactification of orthogonal group, which is a monoid.
So I cannot see it over R like the standard orthogonal group.
You don't see this over R.
Yeah, very interesting.
Well, formally everything can be said over R as well,
But it will be.
but then, well, for instance, if you start with positive definite, yeah.
So anytime, the next example.
Yeah. Okay. And probably the second claim for this one, any Lagrangian equivalent relation can be written as E, which is idempotent, composition with gamma alpha for some alpha. Well, the composition, of course, is not unique. Well, that's all that I want us to know about linear Lagrangian relations. Now, what is a Lagrangian equivalence relation? Lagrangian equivalence relation is not linear, otherwise we won't go far. Lagrangian equivalence relation is A, which is union of L alpha in V times V. Well, there is some subtlety here. I am only interested in finite unions. Non-finite unions are also important, but I don't want to think what restrictions to impose, because otherwise you can take just V times V and say that it's a union of continuum of Lagrangian subspaces. Okay, so more or less finite. Okay. So I will say finite, but you know that sometimes it's, at least my wife claims that sometimes non-finite are very good as well. Okay, so Lagrangian equivalence relation is such guy, such that first L is an equivalence relation, and second, L alpha are linear Lagrangian. those who studied at the university can say that this means that one of them is the diagonal, and L alpha belongs to L, then L alpha to the minus 1 belongs to L, and L alpha times L beta also belongs to L. Okay. Symmetric, reflexive, and transitive. Okay. So these are the conditions. So a nice example of Lagrangian of this guy is provided by theory of finite dimensional Katz-Moody Lie superalgebras. Let me explain. So, we have, well, a Lie superalgebra with Cartan. We have V, which is H star. There is a finite now, well, there is a form, an invariant on V. And there is a collection of, finite collection of roots. And among them, there is a collection of isotropic roots. And here is the result of, well, I will attribute it to Katz, even though I suspect that one should add to it. So, huh? Okay. That the center of such Lie superalgebra is isomorphic by Harris-Chandler isomorphism to C of V to L, when L is generated by the following. First of all, the action of the Weil group, and second, by what I denoted E V0, when V0 is orthogonal complement of alpha. Alpha isotropic root. So this V0, this is Lagrangian linear subspace of atypicality 1. These are, well, Weil group, of course, acts by isometry, so these are atypicality 0. And there is an important addition. Equivalence relation is generated by them. But once you start with Lagrangian subspaces, since when you compose them, when you compose, I don't see where it's written, but yeah, when you compose them, you get still Lagrangian components. So everything generated by this is still Lagrangian relation. You do not immediately see that it is finite, but it is finite, of course. Okay. Well, that's all I wanted to tell about the first part, right? The second is usage of sheaf theory. So let me just say at the very beginning what is the most important way of proving of deducing properties of invariant subrings, as I mentioned. This is, of course, the induction. We have a sort of stratification, and we want to make induction by strata. So first of all, so what type of stratification is it? The collection of all V0s, which are pi 1, for instance, of L alpha, the collection of all coisotropic subspaces in V is something of importance to us. Okay? So this gives a stratification of V, and we want somehow to make induction on the strata. So the most important claim we need is surjectivity of certain restriction map from invariant functions on the whole V to invariant function on a stratum. So this is what this all boils down to. And now we come to
So you talk about proving, so proving of what? Proving of
of subjectivity of certain restriction map.
No, but this you need for what? For the
This will imply immediately the two properties of equivalence relations of this kind that I mentioned.
So like the main theorem that
Yes. And once more, the theorem was known, but it was based on detailed knowledge of generators of different types of.
it was known for Lie, but you prove in general.
For Lie superalgebra. Yes, I prove in general. I don't know whether it's very important, but this is a proof I can somehow understand. Okay, so now, so the second point of my talk is sort of geometric way of looking at this equivalence relation. So I would say geometry. And here the language of spaces with functions was very instrumental. So let me just say in a few words what is a space with functions. So we have X topological space. We have a sheaf of commutative rings. Well, we know what is ringed space. But this one is very special, that this OX of U is a subring of just abstract functions from U to, say, C. So this OX is a subsheaf of this trivial sheaf of disconnected sections with values in C. So this is a formalism that is good for C infinity geometry, complex geometry, I don't know, and algebraic geometry over algebraically closed field, and once you ignore nilpotents and things like this. well, this is disconnected sections with values in C. So the structure sheaf in his formulation is sheaf of functions with values in C. And what is a topological space? You take space of for a commutative algebra over C with of finite type. So you take space of ring homomorphisms to C. So maximal spectrum.
I mean, you have a topology on X, but you don't require the functions to be.
I don't require. No. Now I'm explaining to Volodya what's the difference from the algebraic geometry he studied in Moscow. Okay, so I was also upset, as you are now, when Joseph suggested this as a basic for course in algebraic geometry, but I want to use it now. So, what are nice properties of this formal? I haven't given formal definition. So this is almost all. You have a sheaf of functions, which is subsheaf of this sheaf of discontinuous functions, and you require that if f is a function on some open subset, then d of f, which is subset of U where f does not vanish, is open, and 1 divided by f is a function on d of f. So this is the next condition. Okay. So this is the notion of space with functions. And now, interestingly, if you have XO space with functions, and if you have subset then this induces a canonical structure of space with functions on Z. For any subset. Topology will be induced from topology on X, and this is an exercise to define a meaningful notion of space with functions on Z. I did this in my course at Weizmann last semester. Okay, that's one thing. And what happens, this is precisely as we know in conventional algebraic geometry. If Z is closed, then the map, okay, so you have closed embedding to X, then the map from the structure sheaf to direct image of Z is surjection as a map of sheaves. Well, that's elementary exercise. Okay. Now, on the other hand, you can do differently. You have a space with functions. And you have an equivalence relation on X, any. This defines a structure of space with functions on X mod L. As follows. So choose an open subset. You have a projection, of course, from X to X mod L. And of course, the topology on the quotient is defined by topology on X. And you have an open subset here, U. You have to define what is OXL on U. And you say that this is the collection of functions on OX of P minus 1 of U that are constant along the fibers. Okay. So now I will define the space with function structure on V mod L. Okay, just using this definition. I claim that it's a useful notion. Let us add that, okay, we have L, which is Lagrangian, right? Union of L alpha. Some of them are have a typicality 0, and they are, so this is a subgroup of invertible elements in this monoid. So this defines the Weil group of L. Okay. So, of course, we have a canonical projection from V mod W to V mod L. And this guy is an affine variety. So V mod W is precisely the spectrum in the sense of Kempf of the invariant subring like this. This is a very nice affine subvariety. Okay? What I want to say, what I want to study now is certain restriction to the special. How much time do I have? Some 5 minutes. Okay. So we have V, and we have a collection of special coisotropic subspaces. Those I denoted by V0. Let us assume, this is assumption that has to be verified, of course, in special cases. Let us assume that, first of all, there is a V0 of atypicality 1. And the Weil group acts transitively on the special coisotropic subspaces of atypicality 1. Pardon?
By Weil group, you mean the group of generated by all reflection?
Well, in our case, yes. But in this formal definition, while group is just invertible, is just group of Lagrangian components of atypicality 0. In the example we have in mind, this is, it will be generated by reflections with respect to non-isotropic roots. So,
but this notion is completely general.
yes, yes, yes. Maybe it's not nice to call it while group, but this is the while group in application I have in mind. So it looks very natural. Okay. So my assumption is that all co-isotropic subspaces that appear in my equivalence relation of codimension 1 are, well, W acts transitively on them. Okay, this is one orbit. Then we can so let us denote this space with functions as X, and I will denote Z in X, the closed subset, the image of 1v0 of codimension 1. Once more, V0 is the one that EV0 belongs to our equivalence relation. So the theorem I want to prove is just saying that the global functions on our X, this is the invariant subring we are dealing with. This is C of V to the power of L. A restriction to Z, which is also C of certain V prime to the power of L prime. Let me say what is V prime and what is L prime. V prime is V0 mod V1, and L prime is equivalence relation induced by L on V prime. So this is the induction step. We have something describing center of big of certain Lie superalgebra. This one will also correspond to certain Lie superalgebra, which is obtained if I will just give a name by Duflo-Sirganov functor from the big superalgebra. So it's a smaller Lie superalgebra. And the important step which implies the claim of the theorem, just say that this map of algebras is surjective. And here is the proof of surjectivity without details. So we have V mod L, we have V mod W, this is projection P, and we have closed subset, this is the closed stratum, this is injection I. I wrote that from general nonsense we have a surjective map of sheaves OX to I star of Z, and it's quite easy to describe the kernel. the kernel is P star of O. Sorry, this was W. And this map is multiplication by some element, which in my example was Y. You remember it was Y. So T is sort of W invariant polynomial, minimal one, vanishing at V0. So it's a product of linear polynomials, but it should be made W invariant. So this is a short exact sequence. And of course, it doesn't, what are we, this and this are global sections of these two shifts. So still it remains to prove something, that it's surjective on global sections. But this boils down to calculation of first cohomology of this guy. But first cohomology of this guy is zero just because this is a part of first cohomology of the structure sheaf on a fine variety. So that's the end of the proof. So the proof of surjectivity is a collection of absolutely general fact that a closed subset defines surjection on sheaves plus elementary calculation connected to, well, description of this kernel, which lies in the world of affine schemes, so you have no cohomology. That's it. Thank you.
Questions? Yeah, good question. So, in particular, you give a proof of the Chevalier theorem about usual layers. What do you use it? Or, I mean, if you don't have the even, the what part?
Proof of Chevalier.
So, Chevalier theorem says that restriction gives a surjection.
I didn't know. Yeah, yeah.
I think it's all after Chevalier. You already work with Catan.
Restriction of what to what? I just.
So there's Chevalier restriction theorem.
Yeah, so please, because probably this is question to me.
Well, I will Google and I will answer you. I'm sorry.
Restriction of where functions. This has nothing to do with what is done here because we start from already from the image of Alexander projection.
So you only account for what comes from what?
No. We have to take image of Alexander projection. We know this. We know this from the game description or from general class, which doesn't mean anything about each other. Now we obtain some ring, which is not polynomial, which is round back. But this ring still has some interesting properties, which, well, not interesting maybe, which comes from, which is the same as properties of W invariant. So we want to prove these properties. In particular, we want to prove that any maximum ideal of this ring comes from the maximum ideal of each star.
Which is not completely obvious, you know. And you want to know them if you are interested in, I don't know, describing blocks of representation. Well.
Okay, so I misunderstood
Okay.
I also have a question. Does it now shorten the classification?
No, I didn't. Proof of Shepard-Tod theorem also doesn't. help in classification. No. Classification of simple, basic classical or Kac-Moody, finite dimensional Kac-Moody Lie superalgebras. No, this has nothing to do with this.
I have a simpler question. What is V prime?
Z prime?
V prime.
V prime, great. I wrote it somewhere.
Yes.
V prime is the quotient of V0. You have V. You have a coisotropic subspace, V0. Inside you have its annihilator, isotropic subspace, V1. This quotient, which is of codimension 2 in V, it's not codimension 2 in V, it's dimension 2 less than the dimension of V. It's a subquotient, right? It also inherits this bilinear form. Well, so it's something,
So this is V0 by V1?
Yeah, exactly. Yeah, this is V0 by V1.
For the DS.
Small algebra, which is the first kind of function for bigger.
Okay. Pardon? I never use complex numbers, right? It's just nice letter. Instead of saying algebraically closed field of characteristic 0, did I use characteristic 0? Well, at least characteristic 2 probably would make problems. I don't know. I haven't thought. I don't know. Maybe not. Calculation of H1 need nothing. This is just vanishing of cohomology of a fine scheme. Yeah.
But also implicit characteristic. Developing algebra is not isomorphic, but it's associated graded as a G module. So maybe center is not isomorphic.
Maybe you mean maybe Harish-Chandra isomorphism doesn't work, right? It doesn't. Okay, so yeah, good question. Now I know a bit more.
I have a question.
Yeah.
Can you tell me where you possess use the assumptions on atypicality 1 subspaces?
I do use this assumption. What assumption on transitive action? Yes. Well, otherwise, this restriction, this isomorphism somehow fails. Because actually Z, so this ring is more precisely C of W V0 to the power of A. So you want that W V0 be the whole discriminant somehow. So if you erase all invertible elements, it will still be Lagrangian equivalence relation. But the kernel of the corresponding map won't be generated by one element. Let me say like this. I think so.
Therefore, it will be quasi-affine self-affine or something, so
I haven't thought about this because I had a name where I had a certain aim where I knew that transitivity held. So I haven't thought about this. I don't know how much this question describing invariance with respect to general Lagrangian relations is interesting or important. So for me, the only interesting thing in it is that it describes something people wanted to know.
Thank you.
Thank you. and I should do something with this.